So, fellow engineers, this afternoon, we'll be continuing from where we stopped last week. And we'll be talking about a case study. We've talked a lot. So we didn't do chapter 8. So if you have your materials, you can oblige me by opening your, I'll oblige you to open your material, chapter 8. Chapter 8. So we're talking about system design. We're going to design one typical system today. And that is the system we're going to design is a typical community. If you open the PDF called branch system, this is how a layout looks like. Yes. So as a consultant, your client has called you and requests that you design a water reticulation system. And he has given you all the information you requested for. Last week, I told us that one of the most important information you need is the layout and the topography. Why do you need the layout? Because you need to know where you're going, what you're designing for. Then why do you need the topography? Because with topography, you'll be able to know where to size your different components. Typically, the storage tank will be at the highest. Are you seeing my screen, please? I guess so. Right? Yeah. So this is a typical, so the layout and the topography, that's what we said. Number 2, after layout and topography, you talk about the water user. You estimate the water consumption. You do the estimation of the water consumption based on the demographics, based on the land use, based on the type of building, based on the standard of living, based on the population growth, based on the expected development. So you expect to have done that. Then the third one is you now the second one is that you give a description of the area. Yeah, describe the area, talk about the lowest point, the highest point, where your water source is going to come from, and so on and so forth. Then after doing that, you now do your water calculation, water demand estimation. Okay, some of these words can be used interchangeably. Water demand estimation, water demand calculation, and every other thing that has to describe the place. The third thing now, if that's the fourth thing now, is that you now draw your distribution network, right? After you draw your distribution network, you now analyze it. So we're going to take them one by one. So number 1, we have our layout. The black dots you are seeing are the houses, and in between them is the roads. So this is a perfect and a typical layout or map that you need. Why? Because it has elevation or topography. So in other words, merely looking at it, I already know where I'm going to place my upper storage tank, right? Of course, the water source is going to be at the lowest source. So I will pump using the transmission network from the water source to the upper reservoir so that water will be distributed by gravity. We all know and agree that 90% of water reticulation systems are done by gravity. Why? So that you can save energy. If you don't save energy, then the cost of the water will be so high that it will not worth it. So I have my map, I have my topography. So what next do I do? I'm going to describe the area. I will talk about the people living there, how they are living. I'll describe the area, I'll describe where the sinks are, things like landfill. I'll talk about the geology of the place, right? I'll talk about the rivers, the stream. I will try and justify what to use. Am I going to use surface water? Am I going to use groundwater? If I'm using groundwater, why? If I'm using surface water, why? Are there cost-benefit analysis? Are there things to do? That is what I will do in chapter 2. After that, I'll move to chapter 3. And chapter 3 is now where I will do my water demand estimation. So the next thing I'll do is to come up with a sheet like this. I call it calculation sheet. I'm trying to rotate it, yeah? This is not the typical PDF, I know. Okay, this is it. I want to rotate this page. I don't know what it's telling me.
Sorry, just go to view. Click on the view.
Okay. I might have to close and open with PDF. I'm not just ready for this.
No, it's okay. Just click on view and rotate.
Yeah, I know, but there's nothing there.
It's there now. Sit on
Okay,
the first.
so it's all right. It's all right. Somebody is muting and unmuting himself. It's not. Okay. All right. Branch system. Open with Adobe. Right.
No, first scroll, view, first up, the next one, see. View.
My WhatsApp is, my Zoom is closing it. Of course, that's it. Rotate. Yeah. It's all right. My WhatsApp Zoom icon was blocking it. So I couldn't see. I was only able to see the second tab. So take a look at this. You are expected, in ideal case, to come up with a chart like this. And this is how you're going to do your calculation sheet. In every water reticulation system, you need about 4 parameters. You need 4 parameters to design any hydraulic network. Because the end product of our design is to develop the pipe sizing. That's all. Water reticulation is about what type of pipe do I need and what type of pump do I need. That is it. But the process of knowing the type of pipe you need, the size of pipe you need, will take a whole lot from you. So 4 things you need, 2 of them has to do with pipe. I call them 2 pipe parameters. I'll explain why I call them pipe parameters. And those 2 pipe parameters, number 1 is you must know the length of the pipe. And number 2, you must know the diameter of the pipe. So you must know the length of the pipe and you must know the diameter of the pipe. So these 4 important parameters. Engineer Bolahan, please, you and Engineer Koka, you will not unmute yourself again, please. It's very important. Thank you, sir. Now, the other 2 parameters you need, I call them node parameters. This is very important. You know, I've been teaching this class for a very long time. And I tell you, I have this simple way of bringing this point home, making you grab it from a layman perspective. So the first node parameter you need is the elevation. So in other words, you must know the elevation of every point. Not every point, the elevation of each point, each discharge point, right? Elevation of each discharge point, you must know it because that is what will help you to determine the pressure at that zone point. If you see that the pressure at that point is 0, it means the water is not flowing, right? The number 2, you must know the water demand at every node. So pipe network is made up of nodes and pipes. Nodes and pipes. This is a typical network. This place is a node. This is node 2, node 3, node 6, node 5, So these nodes could be sited at every point where tentatively there's going to be a water meter. In ideal case, in developed countries, in standard designs, the node points are like indicative of where possibility of a water meter can be. And so that means those will be at street joints or in front of your house. If you're living in Abuja in area 1, you find out that the water board people will just put the water meter in front of your house. So every house will be metered. So that could be a node. Then after putting them in front of every house, they also put it in front of every street. Because some houses are not metered based on unit house. It is metered based on subcatchment. So if they come, they just meter like 100 houses. When the bill comes, they'll divide the bill by 100. Everybody pays the same thing. So that helps them not to have many meters, right? Or let's say a community or an estate. If we decide to pipe water in whole estate, we might decide not to put meter, not to bill everybody individually, but we'll bill the entire estate. So when the bill comes, every house in the estate will have their own bill, right? So these are nodes and these are pipes. So this pipe, node ST is where the storage tank will be. This is node 1. So this section is now called ST to 1. Why this one is 1, this one is 2. So this section now we call pipe 1, 2 or pipe 1 to 2, right? So this will be pipe 2 to 3. This is pipe 1 to 4, pipe 4 to 8, pipe 8 to 7. So you will see that the beginning is a node, the end is a node, and the section is the pipe. Now there's no standard how length this pipe will be. But as you all know, for metering purposes, it should be done such a way that there will be aggregate demand. If we're able to aggregate the demand at every section. So let me go back to my whiteboard. So these are the parameters you need. It's very important. So if I want to model a water reticulation network, if I want to start, I'll ask myself, are these 4 parameters available? Do I have the length of the pipes? Do I have the diameter of the pipes? Do I have the elevation? And do I have the water demand? Now, the good thing is this. Some of these parameters, you will get them yourself. Some, you have to calculate it. For the length of the pipe, if you give me a layout, if I scale it very well, I can read out the length of each section and put them down into a table format. But the diameter, I must design it. That's where the engineering comes in. For the node parameters, once I send my surveyor to go to site and take the elevation, the spot height, the coordinate of the place, he will come back and give me the coordinates. I automatically have the elevation. It will help me to know where to locate my overhead tank and help me to know how best to design my network such a way that I will keep moving from up to down, from higher elevation to lower elevation, such that I will maximize the head I have. Assuming I have a head of 50 meters or a head of 20 meters, I will customize my design in such a way that because 50 meters is like 5 bars, let's say 5 bars, yeah? So it means I have 5 bars available in my network. If I don't design it very well, I'll end up losing half of it. And I need it so much because that pressure is what is pushing the water. That pressure is what is pushing the water. So if I don't have pressure in my network, then I have a problem. So the little pressure I have, I must find a way to optimize it. Very, very important. So gentlemen and ladies, anytime they want you to design a network is complete if you have these 4 parameters, right? If you have the elevation and the water demand, and you also have the length and the diameter. Very, very important. So if you look at this network here, what are the 2 things you can see here? Node and pipes, not that thing. There's not that thing in this network other than nodes and pipes. So if you come to this table, I will show you. Here is the length. So the length is normally available. You can easily read off the length anytime. Then This is the discharge. We're yet to do it. This is the slope. We need the slope to read off the size of pipe from the chart, because slope is directly proportional to discharge. The higher the slope, the higher the discharge. Yes, depending on what direction you're moving. The next column is the diameter. This is the symbol, the diameter. Then these other ones are just academic calculation. I'll show us how to do it. Like this was I real. So from I, you can get the I real. Then H is the losses, but you don't need all those ones. Then this is the aggregation of the losses. But what you need is the elevation. So you have two parameters available here, and you need to find the other two parameters. What are those two parameters available? Can somebody answer me? What are two parameters out of the four you are seeing here? What two parameters can you see in this table?
The length and the elevation.
Length and elevation.
So which other two now are we going to look for?
We're looking for discharge and
water demand.
We need for demand and
thank you. We're looking for the water demand, which is Q. Just say Q flow.
And the pipe.
For water experts, I'm going to say three words. Yeah, I'm going to say 3 words. Yeah, diameter of pipe. Yeah, diameter. I'm going to say 3 words now. All of them mean the same thing. Whenever you're talking about water, discharge, sewer, sewage, drainage, gas, fluid, anything fluid. You always hear discharge. Thank you, sir. The next thing you hear flow. The next thing you hear in water, we call it water demand, right? In stormwater, we call it runoff. Am I making sense? In sewer, we call it sewage flow, or discharge, or we call it wastewater flow. Gentlemen, all these things I mentioned now, they mean the same thing. It all depends on what you are referring to. If I say water demand instead of saying sewage flow, then I'm saying the same thing, but completely opposite direction. Because in water demand, in water reticulation, you are taking water from the ground, you consume it. So you take water from the stream, you consume it. But in water sewer, you are discharging based on human anthropogenic activity. You are not taking it to treatment plants located somewhere at the lowest point of the city. But in water demand or potable water design, you are taking water either from groundwater or from a surface water into for consumption. After consuming it, you now discharge it. So for you to get a pipe size, you must first get the discharge. So that's the trick. So as soon as you get these 4 parameters, you are done with the design. The next thing you need to do is now go to your AutoCAD map and then detail it. But the calculation sheet will be done in this format. So take cognizance of this format because it's very, very, very important. So the next step now I'm going to teach you or show you is how you can calculate your discharge in liters per second and calculate your diameter in millimeters. Midway, you will need the slope to aid you. The difference between the vertical over the horizontal, because that slope has an implication on the frictional flow. It has an implication on the friction and on the size of the material. Basically, generally, pipe diameter is how we write it, is a function of the discharge, the slope, and the frictional factor or roughness. These are the factors. So if you remember in our mathematics, I don't know how to write here. pipe diameter, the symbol. This is zoom. So pipe diameter, for you to get the pipe diameter, means you need the slope of the area or the flow between the beginning and the end of the pipe. You need the frictional factor, the frictional material of the medium of conveyance, or you need the frictional factor of the pipe, or you need the frictional factor of the channel. Assuming you are doing runoff, you need the frictional factor. That's what we call the Manning's end. So there are many formulas to get that. We have the Chesney-Manning's one formula, we have the Dashi-Weisbach, and we have the Hesse-Williams. These are all different factors you can use, but all of them mean roughness factor. But then, if you don't have the roughness factor, you can assume it. If you tell me I'm going to use a PVC pipe, I know I'm going to use 0.1 as my roughness factor. Then for slope, if I don't have the value for the slope, I'll use the worst case scenario. And the worst case scenario is about 4%. So, and if I do that, it means the pipe is just a function of the diameter. It's not a function of the diameter. That's all. So the bigger the diameter, the bigger the discharge, the bigger the pipe. That's what it means. So to help us understand this now, let's go to chapter 8. Can we open chapter 8 of our material? If you don't have it, let me know. This file is called branch system. Branch system, and these are the basic parameters we're going to be using. It's a city plan, including road network, contour lines, building. The maximum discharge for the population is 12.4. How do we get this 12.4? Let me give you an instance now. Let me say I have a 3-bedroom bungalow. How many people do you think can stay in a 3-bedroom bungalow? What is the size of the household? Let me say 10 persons. So if I now want to decide, and I will now ask myself again, what is the average water demand per capita per day? What does one person need in a day? Yeah, last week we discussed it to say between 100 and 150 based on the WHO standard. And I even showed us how we came about that 150. You need about 6 liters of water to drink. You need about 50 liters of water to wash toilets. You need about 50 liters of water to cook. You need about 50 liters to wash your body, and so on and so forth. So at the end of the day, it will be around 100 or 120 liters. That's just it. So, and then, so that means the average water consumption per person is 100. That is even the value we use in design in Abuja. It's 100 liters per capita per day. Now, I will explain to us why I insisted on putting these symbols. It's very important. In other words, what this means is that one person will need 100 liters of water in a day. That's what it means. The next thing is to ask myself, what safety factor will I use? All of us know that engineering is a science of approximation. Nothing is cast on stone, nothing is fixed, it's relative. So I will have what I call factor of safety. But this factor of safety is not something I will just choose arbitrarily. Based on the code and standard, there are standards for it. But the factor of safety is between 1.3 and 2.3. That's for hourly safety factor. In other words, it means even if I'm doing any design, when I finish, I will multiply by 200%. I'll explain to you why that's important. Or I'll multiply by 130%, which is 1.3. I must mark up. In infrastructure design, it's better to over-design than under-design. It's better if you over-design, good. In 20 years, that means the project will last beyond its lifespan. But if you under-design, sooner or later, everything will pack up. So, for the purpose of this, let me use a safety factor, right? Normally in his water design, we don't call it safety factor. We call it in sewer and stormwater, we call it peak factor, peak. So whenever you hear peak factor, it means at the worst case scenario, sort of. So let's use 2.0. Abuja, they use 2.3. When you multiply 100 by 2.3, you get to that. So people erroneously say that the water demand, the capital of Abuja is 2/3.
Bye, Zuba. Bye-bye.
Still with yourself. All right. Now, I guess that is well understood. So peak factor of 2.0. Therefore, water demand of the 3-bedroom will now be the demand for one person so now be the demand of one person, which is 100, sorry, multiplied by number of persons. I don't understand what's happening. Okay, times the total number of persons times the safety factor. You understand? If there are 10 persons in the 3-bedroom and one person is consuming 100, what is total demand? It is 10 times 100. But then you also have to multiply by safety factor by jacking it up, because that's what the standard says. The standard says that you must design in excess in case if there are changes, in case if there are losses, right? So if you do this now, what do you get? You get 2,000 liters so that will be 2,000 liters per day. I want to take note of those units. Very important. It's good to take note of units as engineers. So 10 is in capital. This is 10C. I can put C here. Right? So if I multiply this by C, the C will move on. So they need 2,000 liters per day for a 3-bedroom flat that has 10 people inside. And if you look at this very well, this also means 2 meters cubed per day. The reason is that 1,000 liters makes Is that right? So, but in water reticulation design, we are not talking in terms of day. Day is such a big discrete variable. It's a big variable to deal with. So we need it to be in the smallest possible variable. And that will be, we need it to be in liters per second. It's in liters per day. That is for storage. So if we remember before in our school days, one day to convert day to seconds, it will be 24 hours times 60 minutes times 60 seconds. So if you calculate this thing very well, you'll be getting like something like 86400. Put in your thinking card, your memory card, Remember in hydraulics, we got something like this. Therefore, to convert these 2,000 liters to liters per second, I'll simply divide 2,000 by 86400. Whatever answer I'll get will be in liters per second. And that's exactly what I need. That's exactly what I need. $8,600. It will give me
0.0231.
Okay, let's leave it at 2 decimal place. 0.023 is now the water demand for a three-bedroom, a house of 3-bedroom, yeah. If the house is 20 people, that means I'll simply multiply this by 2, and so on and so forth. So that is it. Now, this is what I've done, and this is what I've gotten, right? So when I get this, and somebody says in a whole street there are about 100 houses. If there are 100 houses, I'll either do the same thing by saying 100 times 100 times 2.0. It will give me the same thing. If I say 100 times this, so that will give you 20. Okay, so that is that. We have, yeah, 20,000 liters a day, which is also can be written as what? 20 cubic meter.
But the 100 is houses, so you're supposed to use the approximate number of people per house, right? Not the 100 houses.
Oh, wait. Okay. Oh, so it will be 100 times 10. Yeah. Thank you. Yeah, I'm making sense. So, wait. 100 houses. And each house has 10 people. So the population equivalent is
100 times 100 times 10.
Yeah. So if
I think
so,
you want to
let me
say
just say
100 times 10.
Yeah, or these 100 houses, the way you put it technically, to say I'm designing for 1,000 population equivalent PE. Whenever I see something like this, no, we normally use in wastewater, but that's what it means. So 100 houses simply means why? Because there are 10 people per house. So technically, our design is we're designing for 1,000 population equivalent. So I will simply eliminate this 10 again and just leave it at this. So this 10 is my population or number of persons I'm designing for. I know they are fragmented into 10 houses, 100 houses, sorry. Then this 100 is the water demand per person. And then this 2 is the factor of safety, peak factor. Peak factor, there are 2 peak factors that occur in a day, morning and evening. I think we discussed all those things yesterday when we talked about the demand pattern. The typical household residential area have peak in 2 places, peak at 2 different times. Between the hour of 7 in the evening and 9 o'clock, when people are back home, cooking, bathing, doing all sorts of things. And then in the morning time, between 7 and 9 again, when people are preparing to go to work, they need to take their bath, they need to bathe everybody, they need to cook, they need to even take some water to the office. So this is it. But the thing we are here is that at the end of the day, you must get your answer in liters per second. So instead of me killing myself in all these things, for the 100 houses, I'll simply say 100 houses times the demand of 1 house. And what will it give you?
To give you 2.3.
2.3.
2.3. liters per second. It means that if I'm doing a design for a house, for a street that has 3-bedroom bungalows, and there are 100 houses, it means I will need to the total volume of water or flow or demand, right? That node at the beginning of the street, if I put a water meter there, every time I go there, the water meter must be telling me that there is 2.3 liters of water flowing to meet the demand of the residents of that estate. This is what it means. And what it also means is that the pipe size must have the capacity to convey this kind of huge flow. If you cannot convey it, there's a problem. If you cannot convey, that's why you as a designer, you as a consultant, you must calculate this thing. And then when you get this thing, which is now your Q, right? So if you remember our engineering, Q is A, V, A surface area times velocity, right? That surface area is now your pipe diameter. While the V is the velocity of flow, which you either assume or you use the slope factor to get it. Normally, we assume it to be 2 liters per second, 2 meters per second. That's the average flow of water. So once I have the 2 meters per second, I can easily decide, make A the subject of the formula. Then my A will come up. When my A comes up, I will not use the surface area of a circle, which is pi r square, right? And make r square the subject of the formula, and at the end of the day, I get my R. That's V if I'm using a circular pipe. If I'm using a rectangular pipe, I will know that this A is length times breadth. No, length times length, because it's a square. Okay, if it's a rectangular, length times breadth, whatever. So this is the general way to do the design manually. So once you get your Q, that Q is a function of AV, and your job is to get your A. But in our own case, we have thousands and millions of charts developed by different institutes, developed by different universities. The one we're using today is the one developed by University of Stuttgart in Germany. But you can have anyone. In fact, it's not even by the university, it's by one institute, Institute for Sanitary Engineering. I think I've shared it with us. So if you now go to that chart, it's called a nomogram. There is the one for 0.1, there's the one for 0.4, and there's the one for 1.0. All of them are dependent on the type of material. So for here, we're using PVC pipe, which has the lowest frictional factor. We're using, what do you call it? PVC pipe. So this is what the chart looks like, the nomogram charts. So here you have the horizontal and you have the vertical. Somebody say, is there a standard that states the range of factor of safety and peak factor? Yes, there is in the standard, and I mentioned it is 1.3 to 2.3. But it depends on like Abuja, they use 2.3. And that's why Abuja appears to be still working, because 2.3, they use the maximum. So that's not the maximum. It depends on the number you are designing for. And that is in our material. It's in the material I've shared with us. So now, let me show you how to read this chart so that we can read off this chart and know the pipe size, 2.3 liters per second. And that will mean we have designed that pipe, that particular pipe. So I'll open the chart, which is a nomogram chart. Here you have on the taskbar, you could see frictional losses in pipes. Okay, 0.1, right? On the horizontal is the discharge. On the vertical is the slope. So with the slope and discharge, you can start the pipe. Any question?
Can you
Sorry.
share your screen? We can't see the
Yeah.
chat.
Goodness me. Okay, please also open it. This time is a practical thing. Open it on open your same material in your own so that you can be having a feel of it. Let me increase this to 25%. So on the horizontal is the discharge in liters per second, which is the smallest unit you can ever get water. On the vertical is in per mil. I will explain. Look at this very well. This is 0/00. This is not percentage. So, but we know that our slope always comes in percentage. So what you do is simply multiply this by 10. Any question? Also, the vertical is the slope. So when you have a discharge and you have your slope, you now read off the pipe size. So this diagonal line represents the size of pipes: 100 mm, 5 mm, sorry, 125, 50 mm, 200, 250, 100. So for the one we have in mind, then if you get to any point of pipe, if you come in between two pipes, you choose the biggest of them.
Sorry.
Well, you have your hand raised. Can you answer the question?
Hello, sorry. Yeah, the other line seems that one represents velocity.
Yeah. So this chart now, you bring two velocity, you bring two parameters.
Sorry, sir.
It will give you two parameters. Yeah.
Sorry, sir. I've not asked my question.
Okay, it's velocity. Hold on before you ask your question, sir. So if the thing falls into here now, you get two parameters from there. If you move up to down, left to right, you get velocity. If you move down to up, from left to right again, you get the pipe diameter. So ask your question now, sir.
Okay. So in the
No, we're not exact. Our job is to get you something workable, something within a defined safety limits, right? When we say the load on this beam is 50 kilonewton, who told you it's 50 kilonewton? How did you know? Is it an assumption you made based on empirical evidence? It could be 49, it could be 51, it could even be 70. But you have, as an engineer, you've already used the worst case scenario. You've seen what is best. You've already built in your safety factors. So that's why in this pipe pricing, once you fall between two pipes, you are advised to choose the bigger one. Then why is velocity important? Yeah, last week I told us that the minimum velocity is 0.3 and the maximum velocity is what? 3.0. So you must make sure at every point that your velocity does not exceed these two extremes. So that's why you need to check. So getting the velocity is like a check. Oh, check. To check that, okay, at that station, the velocity is normal. But the most important parameters, takeaway parameter, is the pipe diameter. So let's do for this one. Let's design for these 100 houses now. Let's design for 100 houses. So the 100 houses is 2.3. So what do I do? Unfortunately, I didn't have the surveyor's parameter to know the elevation, the slope between the water source and that point at the beginning of the at the street beginning, right? I don't have the parameter, but let me assume that is about 0.2%. Let me assume that it is 0.2%. Now, 0.2% is the same thing as 2 per mil. But you hear this thing called per mil. This is fine. The symbol is 0.00. This is like 1,000. The limit is 1,000. So if I say per hectare, can somebody tell me what I mean? Per hectare. In tens. Per hectare means per 10,000. 1 hectare is equal to 10,000. How about if I say per meter? Per meter is 1,000, is units. Then per I don't know all of them, but you understand what I mean. All right. So 2.3, I'll read it against 2 because that is how this chart functions. You could come across other charts where this thing is in percentage. So if it's there, I'll just go to 0.2. But in this case, I must multiply by 10 and get 2. So I'll take off from 2.3. This is my 2.3, almost close to 2.5. Hold on, I'm coming. Let me get my whiteboard. Hold on, just hold on. Okay, I'll annotate here. So this is 2.3. And I'll take it up. I'll take it up until I get to 2. Okay, I'll now read it against somewhere here. So let me scroll, if I scroll up, that is between pipe size 80 and 100. And we'll say we'll choose the biggest one. So what's the pipe size I will choose? I will choose 100. If I iterate or if I interpolate, I might get something like 90. But all of us know that there's nothing like 90 mm pipe in the market. It's either 55, 100, 150, 200, 250, 300. It comes in that order, 50, 100, and so on and so on. So the pipe size I need for this 2.3 would be something close to 4 inches. Any question on that? I don't think there's any question. So, but for the one that is 0.023, right? For 0.023, if you look at the horizontal, there's nothing like 0.023. The minimum is what? 1. So the standard says anything less than 1, use the value for 1. Anything less than 1, assume 1. Assume the value of 1 liter. Assume the water demand to be 1. So if I assume the water demand to be 1, and if I take it to 20, I'll get 65. Somewhere here, 65. So you could see that I will use 65 mm pipe to pipe into the house, but I use a 4 inches pipe to pipe from the beginning of the street to the end of the street, because I have 100 houses that requires 0.023 liters of water. Is that understood? So let me give us a challenge. Now, everybody will solve this. Normally, we should go for 1 hour, 10 minutes break at the half of this class, but let's fire on. So what I want to do is, using the same thing we did, I want you to design the pipe for 1,000 houses, or design the house for 10 streets. Let me see if anybody will understand the jigs. Design for 10 streets. Each street has 100 houses. Or I'll simply ask you design for 1,000 population equivalent.
Sorry, I can't hear again. I don't know whether everybody's hearing.
Okay. So this will now be for 1,000 population equivalent. So can we do that design?
What is the expected number of people per house?
It's no longer population equivalent. It's not 10,000. Sorry.
Good.
And this would mean like the design for the entire main pipe of the estate. This must be a very big estate that has 10 streets. Each street has 100 houses, and the water demand for each house. We have done it. So can somebody give me the pipe size? What pipe size are we going to use? We have like 5 minutes to do it. I like us to do it. So I'll be confident that we've grabbed pipe sizing. The one we just finished now is for 1,000 population equivalent or 100 houses. Now I'm saying design for 10 streets. If there are 10 streets, right? Who has finished?
How do we get the charts?
It's been sent to you, sir.
250.
It's been sent to, let me send it again. Are you coming for the first time? Just put in the chat box. Yeah, I understand. Some people will not have the chat. So let me quickly put in the chat now so that I'll be confident everybody have done something.
Hello, sorry, sir. I did not get your explanation on the chart.
Oh.
Me, I was raising my hands, or maybe you didn't see me.
Yeah, you're raising your hand, but I
We have 100 millimeter diameter.
Okay. I have closed the chat. Why? Because if I didn't close it, I won't be able to upload it in a Zoom. Zoom is not too rugged. Like, just hold on. I'm on it now. Oh yeah, okay. The horizontal is the discharge. The vertical is the slope.
Sorry, we can't see the chart you are sharing.
The horizontal is a discharge. This is 1 liter, 2 liter, 3, 4, 5, 50, 70, 100, 200, 700, 1,000, 2,000, 3,000, 4,000 liters, and so on and so forth. Now the chart is the slope is in per thousand. So if you have something in percent, which is per 100, if you multiply by 10, it becomes per thousand. So if you are giving slope in units, if it's unitless, you multiply by 1,000. But if it has units, no, whether it has units or have units, you multiply by 10, please, not by 1,000. Right. So here, I hope others are doing the assignment. I'm just reviewing for those who are just coming. So here we say 2.3. I have to read off 2.3 until we get to the slope, which is 2. So it's now closer to 100. It's between 80 and 100. And therefore, we choose 100. So when I choose 100...
Sorry, where do you have the 80 and 100?
This diagonal. This is 80.
Please, if you can palm down so we can see, because the 80 seems to be hidden.
Yeah, because if I pan out, the bottom will disappear. Right? Yeah, it's working now. So this is 2.3. Take it to 2. It will fall between 80 and 100. We use the higher one. But later, I'm going to show you that in choosing the higher one, you must not over design. So you must do what we call percentage filling. You need to check how full is the pipe, because the standard is that your pipe must be 70 to 90% full. So don't go and design a pipe that is carrying capacity at 30% or 40%. You're a bad consultant, you're a bad designer. Your pipe must carry 70% of its load or up to 90% of its load. Only 10% free board you should give. So back to the question now. How many of us have solved it?
Sorry,
Go
my
ahead.
assumption is that the slope is two as was used earlier, correct?
Yeah, because I didn't tell you what the slope is, because it's not design, right?
So we are assuming 2 then.
You assume things because you need to read off from something. But if it is a redesign, this is where your surveyor comes in. This is where the first person that goes to site, if you want to do infrastructure planning, is the surveyor. You either go with total station or with GPS and get you those information, those data, those road data. Then the waterman will pick it up from there. Zainab says 600 millimeters. Zainab, check what you've done. That is way too high. Olubenga said 250 millimeter. It sounds more like it. Getting a 600 millimeter pipe in a water reticulation, that means you are designing for the whole country or the whole city. So, but we are talking about 10,000 population equivalent or 10 streets, okay? Making up of 100 houses per street. Someone said 230, very good. Someone said 200, good.
But the liter per second is not supposed to be 230. That's for the 10,000 population.
Yeah, but I can't see 230.
It's actually 23.
Here.
23?
Well, that's the discharge. The discharge is 23.
Yes, the discharge 23.
Yeah.
Liter per second.
Yes, then therefore, what is the corresponding pipe size?
It falls between 200 and 250. That's about 230 from my own side.
Okay, that's what it is. So what will you use? How close is it to 250 and how close is it to 200? Somebody says he's using 230. I wish you well. I only pray that you see a 230 pipe in the market.
It's very close to 200, sir.
Wow, we use 250 then.
The person that got 200, what charts are you using? Are you using the chart for ductile iron or for concrete pipe? I suspect you're using this pipe for, or is it the pipe for PVC?
Yes, for PVC, sir. I'm using the same pipe. The same chart. I think the same chart they're using.
Okay. And you got what?
I got in between 200 and 250, but it's closer to 200.
All right. Now let me show you guys something.
True.
Okay, let me show you guys something you need to put into consideration. Because sometimes you don't need to be a bad designer. You must be good. You must do what we call optimal design. You must optimize your system. It's not just say, I went somewhere last week, for those of us who are civil engineers, I saw somebody using 25mm to build one floor. I almost wept. 25mm, 20mm, right? Yeah, 20mm. Now, it's good. He has money, or he's ignorant, whichever one applies. But you and I know that if you're a good engineer, you use 16mm, you get the same results. Am I making sense? So the person that is using 250, I think this must be one of us. Just hold on 1 minute. So this is how to use the chart. So now let me just show us something very important to make you understand how this thing works. Now let's assuming that this is a pipe. And designer A designs his water. And the maximum level of water is here. And designer B designs is water. And the water level is here. In other words, all this is water. Sorry, this is B, and this is A. Who is a better designer?
For me, depending on the return period expected, if it's a critical project, you want if it's a project you want to use a very high return period, then A will be okay. But if it is something that the return period is not that much, B will be okay.
Okay, let's assume now that we are talking about P factor. In water reticulation, return period doesn't come in. The return period comes in storm design, flood design, and stream flow. Now this is pipe work, which is simply water reticulation. Let me draw this one. Let me give them the same drawing. I just want to point out something very, very important. Just like the instance I just gave now, somebody is using 25 mm for where you can use. So this is the level of water.
B is better.
B is better because B has an optimal design. He has designed the system, and that's why, based on the code, I keep saying that the code, this is German code, right? Don't quote me. Now, it says that for you to have an optimal design, we expect your water, the carrying capacity of a pipe or the water level, whichever, two of them are the same, must be between 70 to 90%. So, but this person is at, this is about 20 to 40. So it means that if this pipe is 250 mm, then this designer should use a pipe of, say, 150. But because he's using the same pipe of 250, now look at where his water is. I don't know if that's making sense.
I think based on the code which says 70 to 90%, that means that B is a more acceptable design.
Yeah, that's just the point. Because the implication is that if this 250 mm pipe will cost 8,000 per meter length, and you now want to use it here, whereas this one, that's 150, should cost like 4,000 per meter length. You can see that, and everything is about the pipe. If you talk about water reticulation design, if you calculate the pipe, you've got 70% of the total cost of the project. Because from the length of the pipe, you're going to get you're going to get the length of digging, you're going to get the depth of digging, you're going to get the length of blinding, you're going to get the length of backfilling, you're going to get the if there's a hunching, it's going to get the volume of concrete for hunching. If you're going to provide valves or everything just depends on that single pipe factor. The other thing you need to design is maybe the pump and the pump house. But most of the cost goes into the pipe and what it takes to lay the pipe. The labor cost will be based on the pipe length, right? The excavation cost will be based on the pipe length. So you can see that getting this length of the pipe is a very important parameter. And that's why I said at the beginning of this class that everything about water reticulation is about hydraulics. And everything about hydraulics is about pipe sizing. That's it, just to size the pipe. Why? Because you need the right type of pipe size to safely, efficiently, conveniently, and cost-effectively convey a certain amount of water. Okay, Engineer Timothy, your hand is raised.
Yeah, so my question is, where does population rise come into the equation? I'm just thinking of these two scenarios that you just presented. I'm looking at I'm looking at a situation whereby, because it boils down to maybe, hello, can you hear me?
Hey, sir.
Fine. So it boils down to what maybe if the community or if the government responsible for this design perhaps is a municipal water supply that they are trying to install for the community. Now, if you are talking of population increase, one would think that to have a pipe that is presently underutilized will save them the cost of having to do it maybe in the next 20 to 30 years when the population must have increased and the volume of water demand must have increased significantly. I'm just thinking whether that also comes into the equation when you are considering the size of the pipe. For an individual, if I have a duplex or a bungalow, it's not likely that I'll exceed a certain level of population. But for the pipe that is probably running along a major, maybe a major arterial road or something like that, that will have to continue to supply to maybe some undeveloped area that will end up getting developed in years to come. I think they will also have to put that into consideration in the present size of the pipe that is being installed.
Okay, thank you very much. Let me just ask you, you're in the last class?
Wasn't, unfortunately.
Yeah, that's why. I know. So in the last class, this is where we started. We said this is the steps for water reticulation design. So we said the first step is you have to get the map or develop the map or buy the map or send somebody to go and get you the map or design the map. Then you have to go and do a reconnaissance survey so that you can describe the area very well. Your clients should be able to read your report and have a visualization of what you are talking about, right? Then the second one, we say description of calculation basis. You see that 1,000 population equivalent, that 10. I purposely use that 10. There's no 3-bedroom house that has 10 people. So I'm using the projected population. So that's where population comes in. Before you arrive at your final population equivalent or catchment size or catchment characteristics, I'll still come to that in terms of the land use, you are supposed to have optimized all the variables. And there are 3 of those variables. What is the water demand of different users? You don't just say everybody will use 100 liters per capita per day, rubbish. You have to look at the sectorial consumption. Number 2, you have to factor in the expected growth. So for a 3-bedroom family, I know 8 people, 7 people will do, but I have imagined where in 20 years' time, depending on my design horizon, I have designed 30 years. So I'm assuming by 30 years, two more people will join the family, whatever, right? And that's why we said you must do population projection. You don't design. If I'm doing a design and they ask me to do a design that will last for 50 years, it is the population of 50th year that we use in year 0. So the infrastructure will live to meet up. And once it reaches up to 50 years, it will have reached its lifespan. So if it fails after that, I'm justified. Then the other 3 key parameter is future development. Last week we talked about what all of us face in school, right? Yeah, Timothy, you know what you relate with this. When they develop the school, they have hostel A and hostel B. They never knew that TEFON will give them money for hostel B, C, and D. So they did a pipe size based on population of students of 10,000. 5 years along the line or 10 years along the line, the population of the students increased to 20,000. What will you see happening? During peak hour, people in hostel D and C will not see water. Why? Because the pipe size was designed to accommodate only hostel A and B. Unless you create another independent system for them. Unless you create another independent system for them, right? Or a new decentralized system, If you are based on that old system, that means you probably have to come back and excavate, or you no, not excavate, sorry, you do a new piping. That means there will be a new piping going to stage A and C from the tank. But you cannot just go to the dead end, the end of the last pipe, and continue. No, you don't do that. So the population have been factored in ab initio before you arrive at that value of population equivalent. Okay, I think we are making progress. So we have designed for the 1,000, all of you got it right. So we now move. So now let's go to what we have for today. So this is all what you have, you see? Now, this is like tutorial, we're starting. So this is steps you need to take. Now, first of all, do the water demand calculation. So I've shown you how to do the water demand calculation. Population is, the total population is 12.4 liters per second. We just did one for 100 houses and we got 2.3. We did for 1,000, we did for 10,000, we got 23. So this should be like, let's say 5,000, right? Which is like half of it. So this is like a 5,000 population equivalent. But the industrial area is also consuming 5 liters per second. And I have been told to design for firefighting. Firefighting for 2 hours, I will need about 48 liters of water per hour. That translates to about...
Sorry, I don't know whether you are sharing the screen. I can't see the screen.
Yeah, me too.
Chapter 8. Chapter 8. Go to your course material and open chapter 8. This is it. Are you there? So, what have I done? So after doing this, you now follow the steps. So these are the steps you take. I've already mentioned them. Number one, you work out the layout of the pipe. What layout am I going to use? What layout? There are 2 layouts. We'll have the branch system and the loop system. So you need to look at your design and ask yourself, which system best suits me? Based on the, This is the original map. This is the distribution network. If you look at it very well, it's making sense, following the right of way. So here now, if I draw this network and I consider these dotted lines, I will call it a loop system. But if I remove the dotted lines, it will be a branch system. So this is what the branch system looks like. It's the same map. The dotted lines is a loop system. Without the dotted lines, if it's like this, it's a branch. So you can see that this is like a 3 branch. It's branching off. The loop system has an advantage. The branch system has an advantage. There are many of them. They have their pros and their cons. But the branch system is easy to calculate. But the disadvantage is that at the end of the day, you have dead ends that sometimes you might need to put washout valve. But let's not go there yet. Let's do the real thing. So after working out the pipe network, how it will look like, in other words, they gave me this. They gave me this, and I came up with this. So I have worked out the pipe network. The next thing you do is you determine the length of pipes and elevation, which is a way of saying you call up the data from the surveyor, because these 2 parameters can be gotten from the surveyor. The surveyor can give you the elevation of every node. And you can also, from your AutoCAD drawing or from layout, you can measure out, you can read out, you can extract the length of the pipes, and then you go to your table. That table I've given you, or create your own in Excel that looks like this. Right? So that's step 2 is done. Any question? Step 3, you determine the flow rate in each session. That's exactly what I've done. The flow rate in each session. So, for instance, let me give an idea. Determine the flow rate in each session. Let me open another one so I don't have to keep rotating it. Open this file from your system because we need to do some calculation. Get a pen, get a notebook or something to write, a pad or something. From this end to here, this is node 6. This is node 13. Node 6, node 13. Because the third step is that we determine the flow rate in each session. There are different ways to determine the flow rate in each session. I can do it by catchment. I can say every 10 hectares. When I say 10 hectares, I'll say, okay, if the land use density says 300 per hectare, and the hectare I have is like 2 hectares, so that means I have 600 people. Are you with me? Now, if you are doing water reticulation, it's possible that you don't have the layout. The architect have not done the layout, but they can also give you size of the land. Once they give size of the land, assume a probable land use. In Abuja, we have all over the world anyway. We have medium density, high density, low density. The idea of using low density, when they designed Abuja 1980, 40 years ago, nobody knew how many people are going to be in Abuja, but they use land use. They just mark out some areas and say, okay, this area is going to be high density for government workers, for government institution, we'll call it central area or whatever. Okay, this place is going to be Kuje. Kuje is going to be an agricultural zone, right? It's going to be a low density area. Even though now they are beginning to change it to medium density. That's why if you draw your house and go to domain control, they'll tell you to go and build more, put more houses. What they're trying to say is that the land use have changed to medium density. Then if you go to some area, central area, and you say you want to build bungalow or you want to build 2 floors, they will ask you must build 4 floors. Places like Jahi, Kado, along that corridor. That one is for aesthetics. But in some areas, based on the original design of the estates or of the layout, people now need to conform. So Abuja has a master plan. Abuja was designed in such a way that everywhere has where people will stay. Government institution, government ministries, and the design are factored in the water utilization, water demand. So when you now bring your house to build, the people in domain control will now know where your house falls in. And that will be the basis to adjudge your design. I don't know if I'm making sense, but for me, it's like I'm making sense. Okay, now, from 6 to 13, how many houses are there? Or what is the catchment area based on land use? But luckily for us, we have a design, we have a layout. So our job is to say how many houses are here. So if I count these houses, you count 1, 2, 3, 4, 5, 6. There are 25 houses here. I've done it before. Between 6 to 10. Now I'll tell myself what is the value for one house. So now you and I need to agree. What is the size of these houses? So let's assume that these houses are duplexes, right? Or let's assume what you've been assuming, they are 3-bedroom bungalows. So each house is, we've done it before, 3-bedroom bungalows, has 10 people, occupants, 10 capital, and each person is 100 liters. Factor of safety is 2. Therefore, water demand for each house will be 2 times 100 times 2 times 10. And that will give us 2,000 liters per day. If we now convert it by dividing it by 24 by 60 by 60, we'll come up with 0.023. So that means for those 24 houses now, it will be 0.023 times 25. So that becomes the water demand that I will put in node 6. Can somebody help us out with that? Okay, I'm there. 0.023 times 25 houses. It will give me 0.58.
575. Okay, 0.58.
8 liters per what? Seconds.
Seconds.
So this is liters per seconds. Is the flow of, so if I bust the pipe and measure the discharge, this is what I should be seeing. If I want to design this now, only this now, all of us know what it is. I go to my design chart now. Since it's less than 1, I'll use the value for 1. But I need to know the slope. So I have to go back to that chart and get the slope. And it's very, very possible to get the slope because the slope is given. Why can I know the slope? Because I have the elevation. So we're talking about 0.6 to 13. This is 0.6 to 13. 0.6 to 13. 0.6 to 13 has a length of 210 meters.
Sorry, I can't see your
We're not
chart.
seeing the
so I
chart,
don't know whether-
Oh, wow. So this is 0.58 I've gotten. So I will now go and estimate the slope. So to do the slope, what is 0.6? Based on the elevation, this is the Z. This is X. This is Z. So 6 is at elevation of 261. 13 is at elevation of 252. Slope is vertical over horizontal. The horizontal is 210. That's the length. The plan length, how do you call it? The longitudinal length, the horizontal length. Why this is the vertical length of vertical length, yeah. Height, elevation. I'm trying to use road parameters, and it's not working. So 261 minus 252 will give me 9. Then 9 divided by 210 is giving me 0.042. I multiply by 10 due to my chart. Multiply by 10 is because of my chart. If you are using any chart other than this chart, read through the rules and laws of the chart, how to use the chart, right? So the slope in this case is 0.4 per mil, 0.00. Yeah, one hand is raised.
Yes, just want to get something clear, please. So under the column where you have length, at 0.6, you have 110 meters, and at 0.13, you have 210 meters. So
okay,
I was thinking whether we want to get the difference between the two. Like
no, sir.
210 minus 110.
No. Now, if you check the chart again, storage tank 2.1 has a length of 120 meters. That was what I'm trying to do. This is like section this to this, this to this, this to this. So where you do the difference is in the vertical aspects, just like you know, coordinates, right?
I'm fine with that.
Okay.
But
For
I'm
instance,
looking at,
go ahead. I'm listening. I'm listening to you, sir. So
what I mean is, where does the 110 and 210 come into this chart you have?
okay, 110 is section 7 to 6, 576 is 110 meters in length.
That's fine. I get it now.
Okay.
So then from 6 to 13
is 210.
That's the total length. I get it now.
Yes. But when you want to do the elevation, you go to this point, which is the Z value, and subtract from the corresponding Z value of the next one. I was about doing this, right? So, but no need for it again. I guess it's well understood.
Just go ahead.
Please go ahead, sir.
Okay, so now I've gotten the slope as 0.4, right? And the water demand is 0.58. Because it's less than 1, I'll use the value for 1.
Sir.
Ask your question. Okay, because it's less than 1, I'll use the value for 1. And the slope will be what? 0.4. So that will be 100 mm.
To draw you back a little.
Okay, your voice is cracking. Could be network.
So sorry, a call was trying to distract me. I just needed a reiteration on that slope.
On the slope. When you're ready, sir. I think I didn't hear the last thing you said.
Get the slope, please. Can you just explain?
Okay, the slope is from the elevation, right? Now, slope is the difference between the vertical and the horizontal. So this is y. This is y, and this is x. And this is the angle theta. So the slope is the vertical difference, right? Divided by the horizontal difference. In this case, the horizontal difference, the vertical difference is the elevation height. What is the elevation height of this place? And what is the elevation height of this place? So slope here is y over r, which is equal to y over x. X is 210. Then y has two values. One is 261 at the highest point, and lowest point, it is 252. So the difference is 9. Therefore, slope becomes 9 divided 210. And that will give you 0.0442 or thereabouts. But if you come to my chart, you won't see 0.042 because it's in percentage, but my chart is in per mil. So I'll multiply it by 10. So this is in percentage. So I'll multiply by 10. And I will get, what do you call it? I'll get the answer in 0.42. Any question on that?
I thought percentage it is by 100 instead of 10. Hello.
Sorry, you want to mute Paul or Sergeant? I think it's one of you.
It's okay. I'll mute them, please. Please, it's good that we mute ourselves. I know it's not easy sometimes. But it's important. It's all you unmuted again. Hands are raised. Are you asking questions or you put it down? I'm seeing 2 raised hands. You have a question?
Yes, sir, I have a question, sir.
Okay.
Sir, is it possible to get a negative value of slope?
Yes.
Of course not.
No, like what happens?
No, it means you are losing pressure somehow. It means there will be losses there. Water can flow in both directions. That means you need like how do I put it? You can have a negative slope, but it means it's working against your pressure. You know, water reticulation, you have this pressure that you want to maximize. So the more negative slope you have, the more you're losing them.
Does it affect the size of the, or you still use the same?
No, it does not affect size. You see, same value, sir. That's a good question. To have negative slope, it doesn't mean anything. Of course, if it's a pump system, I mean, who cares? The pump will overcome it, right? It will just follow in the rating of the pump. But now, it means maybe you have to elevate your tank a bit more, sort of, right? Maybe by 10 cm or your tank, just to increase. That's just it. Okay. Another question, I guess.
No, my question is that why multiplying it by 10?
Okay, but I'm multiplying by 10 because every chart you use for engineering, we have a certain rules and laws. The rules and laws here is that this chart is per 1,000. Look at the table. Can you see it? 0/00.
I can't see the table.
We can't see the charts.
Okay. Well, you have it. I said download it. I uploaded it on the chat box. I like everyone to open it. As I'm opening mine, you open yours. But I know it's not that easy anyway. Juggling the two. So look at it. This is 0/00. It's 0/00. Any question?
Go ahead, sir.
Okay. So now, all of us have seen how I determine the flow rate in each section, right? Then there are different ways to do it. This one says divide total areas into areas connected to a certain node. Calculate or measure areas. Calculate flow rates to areas respectively connected to nodes. So if you didn't do the way we did it, because we did it this way because there are houses. Now the question is, if there are no houses, if it's a virgin layout, that means you use area. You use area measurement, hectares. How many hectares are connected to node 6, to node 13? That reminds me. If I come to node 13, This value I got of 0.58, I'm going to impute it here in this node 13. It's going to be in this node 13. Then if I compute for the houses lying between 7 and 6, I'll put it in node 6. So I'll continue in that order. So let's do for a second one now, so that we understand how this thing works, because that's where the real thing is. This is node 7 here. Can you see it? And this is node 6. How many houses are between node 6 and node 7? So let us count. 1, 2, 3, 4, 5. 5 houses. But based on what I showed us, future development will tell me that there will be 5 houses more on the left side of the road. Those people who have it are yet to get money to build their own, but I'm going to factor it in already. So between those 6 and 7, I'm going to estimate for 10 houses. So 10 houses. So let me delete everything here, clear every drawing. So we have done for node 13. Node 13, we got 0.58. Then for node 6 will be 10 houses times the value of one house. I don't need to go start doing times 100 times. Right? And that will give me 0.23 liters per second. So it means node 6 is 0.23. Therefore, node 6 will be itself will be node 6 plus node 13. That's the formula for node 6. Why is it so? Node 6 is the node delivering water to node 13. So 10 houses are directly connected to him, but node 13 is indirectly is on its downstream. This is the hardest point of this training. This is the hardest point on this. Somebody said, are we making an assumption for population growth? Yes. Nigeria is 4%. So if you're designing for any city in Nigeria, you design 4% increase. It depends. It depends on whether the population is growing or reducing, or rely on census or land use growth. Yes, you can. It depends on everything. It depends on the unique situation. Let's go. Let's not talk about that now. Let's get this clear now. This is where the real thing is. This is what makes it difficult for people to do this design. So I want you to get it. And let me use one funny analogy to do it. Let me use one simple example to do it. This is a street. And these streets have houses. House 1. House 2. House 3. Right? Now, if 50 liters of water, 50 liters per second is coming here, and this man takes 20. At this point, what we have is 30 fluid. If this man should take 15, right? And no, at this point now we have 10, sorry. Sorry, stay with me. What will be here? What will be the last one?
$20.
No.
That should be 15 now.
15.
That would be
So
It should be 15.
at point 20.
It will be 50.
At point 20, if I ask you what is the water demand here, will you tell me 20?
It's 50.
No.
It's 50.
50.
Yes.
Or the demand for the house is 20. But because there are two guys who need to consume another 30, therefore the demand here is what? 50. So look at node 6 and look at node 13. This is 7 here. This is 6. The water demand for 6 will not be 0.3. Rather, it will be 0.23 servicing these 10 houses plus 0.58 servicing 35 houses. If you don't get this, you miss it the whole thing. That's why I took my time. So this is node 6. Between node 7 and node 6, there are 10 houses. They are consuming 0.023 a house. So 10 of them are consuming 0.23. However, a downstream number of 25 houses acting like a cluster are already taking 0.58 liters a second. Therefore, the node 6 will be itself plus node 13. Right? Now, before I do node 7, I must do node 11. Therefore, node 6 is equal to 0.58 plus 0.23. And what would that give you? 0.81.
0.81
liters per second. If you go to node 7, node 11, what is demand for node 11? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 houses. So node 11 will be node 11 be what? 0.023 times 10, yeah?
Yes.
0.23. Already we know the pipe size. If I've done pipe size for 1, I've done for 0.58, and I got like 65 or whatever, that means this other one will be 65, unless the slope changes. But I don't think the slope will change. So this one will have minimal pipe. So I can make my minimum pipe to be 2 inches, 50 mm. So any pipe that is less than 0.1, that is less than 1 liters, or that is less than 0.58, I will just use nominal size. I will call it nominal design, nominal pipe. I'll just use nominal pipe to make the design is faster and easy for me. But node 7 will be what? Node 6 plus node 11. Of course, plus houses on it, if there are houses connected to it, or I'll say itself, but you understand what I mean. Itself means if there are houses on it. So 2 houses, two external connections are on node 7 already. 2 external connections are on node 7 already. So if there are another houses connected to it, that will become the another load, in quote. So for node 7, what do I do now? For node 7 will now become node 11 plus node 6. Node 11 is 0.23, node 6 is 0.81. Therefore, node 7 will now be what? 1.05 or thereabout. But let me check if the houses between 7 and 8. I'll add it to it. And there are about 1, 2, 3, 4. And if I multiply by 2, it will be 0.18. Therefore, node 7 is now equal to, what is the value for node 6? 0.81 plus node 11.
0.23.
Then the 8 houses connected to him should be like 0.18. So you could see how it's aggregating. That's why, as you are getting closer to the water source, the pipe sizes are getting bigger and bigger and bigger. So we're not going to continue like this. I just want us to understand the concept. Rather, I will now give us the one that we have done, have finished. You now look through it and grab it. Please, it's important that you understand this side of it, this aspect of the whole thing, because that is where engineers get it wrong. And that is what makes it look complicated. So this is our 1.22 liters. When I get to, now watch me. When I get to node 8, I will add the value of node 9 plus node 7. But before I could get node 9, I have to do node 12 and do node 10. Any question? I have it somewhere finished, but I guess it's in the cloud. Okay, node 4, let me quickly do that. Check node 4.
Are you adding it to node 8 as well?
Wait a minute. No, node 4 will be, I will add node 8 plus node 5 plus node 3.
Okay.
And it's small load. That's why as the water is coming, as it's getting more tributaries, the pipe sizes are reducing. I mean, all of us know how stream flow happens, right? Is this one electrical engineer that came to this training said that this is called Kirchhoff's law for electrical engineers. And I agree with him, because engineering is something that all of us started from mathematics. I mean, we started from nature. How do I put it? From basic sciences, and then we apply mathematics. So if you have current, this is how current flows. As current is going towards the smaller loads, the pipe sizes are reducing, because the current, the amperage, which determines the pipe of size, is reducing. The voltage can be the same, because the voltage is the force, is the pressure, while the current is the determining factor for the size of pipe. So the same thing applies here. So any question on that? So let me quickly go to cloud. Have I shared a cloud director? Yes, I've shared. So can somebody check if can somebody see if the thing is there? If the finished one is in, it should be in PDF or Word. This is what InfraLAB water. Yeah, we have it. ABC essay design. Yeah, we have it. We have it in multiple. So branch system design. Can we download it?
Please, can you drop the link to the documents on the Zoom chats?
Yeah, I've done that already. But let me drop it again.
Okay, thank you.
Yeah, let me drop it again. And let me even drop this one now that is so unique. I even asked some questions there. And I think I need to download that a particular one because it makes a whole lot of sense. Because I even asked some questions there. To find my way around this. Any question? We're gradually coming to an end of the class, but not before I make sure I finish this slide. Not before I make sure I finish this slide. So back to this slide. So if you finish this, the next thing you say is a divide network into sections. We've done that already, right? Determine flow rate in each section. Determine beginning and end of section. That's what we have done now, right? Then the next thing, determine the minimum service pressure. Okay, what is minimum service pressure? Oh, we did it last week. Minimum service pressure is what is the base pressure you want for the network. If you are doing a design for where you have 4-story building, you don't use the person at the ground floor to do your design. You use the person at the the 4th floor. The pressure of the person at the top floor becomes your minimum service pressure. Becomes your baseline because that is the person you need to satisfy. Once you be able to satisfy the person living at the 4th floor, the person living at the 1st floor will never have problem because once water is coming, the pressure will reduce as it goes up, right? And you don't want that pressure to reduce. So you need to use the person at the 4th floor to do a design. That's why in Abuja, for those of you that know about Abuja, you cannot design more than 12-story building in Abuja in some areas. The reason is that the tank supplying water to Abuja cannot supply water to somebody whose house is more than 12-story building. But that does not mean you cannot build 12-story building, but you need a special approval, meaning that you're going to develop your own water or you're going to build some pumps so that when you take this water from public supply, you push it up and then it flows back by gravity. So if you are doing 12-story building in Abuja, you're on your own because the municipal water supply will not service you without the aid of pumps or additional conditions. So in Germany, the minimum service pressure in a network is 2 to 3 bars. But anything like 1 bar is okay. Or there's standards. Sometimes standards cannot be met. So you make do what is possible, what is feasible. Then choice of K. Okay, choice of K is just like saying choice of pipe materials. Are you using a ductile iron? Are you using PVC pipe? Or are you using asbestos ceiling, which is no longer being used because it's carcinogenic? Or are you using any kind of materials? All materials in the market have their unique K value. When I mean K value, I'm talking about the roughness factor. Number 5, you discuss about the elevation tank. There are 2 conditions. Either the elevation tank is fixed or it's not fixed. If the elevation tank is fixed, you now have to calculate your slope based on that by saying that the highest point of water in the tank minus your, I hope you're seeing my screen. Yes. Minus the service pressure.
Yes, you can see your screen.
Yeah. Slope becomes the geodetic height of the tank minus the service pressure, which is an imaginary figure, or minus the person living at the 4th floor. That's just what it means. Yeah, the person living at the highest floor. Then divided by the total horizontal length. I mean, this thing simply means head over length. This is just typical slope. Slope is vertical over horizontal. But when you're talking about your vertical, from what point to what point? So this place is saying from the water level in the tank to the floor level of the person living at the highest floor, which is technically called service pressure, or the pressure at which you want the least person to have in your network. It's usually 20 cubic meters of water or 2 bars. But you cannot be fixing 2 bars when you don't have 2 bars as an advantage in your network. This is where you have choices, where to site your elevated tank. So that is that. So what the second thing you see here is the admissible I. One with admissible I, it simply means instead of saying the highest water level or the head difference of water, you should use the lower water level. The lower water level in the tank minus the service pressure minus the hydrodynamic height. So this is like an added advantage. Then the next 17, the same thing you do is you now determine your diameter as a function of discharge, slope, and roughness factor using nomogram table. So that is it. So this other one is if you're working backward, if you now want to determine whether all those ones are met. For instance, you want to check if your service pressure is not exceeded. Yeah, and maximum, okay, we have minimum service pressure and maximum service pressure, we discussed last week. Maximum is 8 bars, minimum is 2 bars. You just don't allow any kind of pressure on your network. There should be a limit to it. If it's more than 8 bars, we say you divide them into pressure zones. Then sometimes, if it's too low, you might provide booster stations. So that is it. So if the elevator tank is not fixed, you simply assume diameter to be a function of the discharge only. Then you say go on with step 8 to 13, like before, beginning at the end of the system. So just repeat this again and again, and that becomes your design. So this is a summary of everything we've done. For a loop system, it's more complicated, and I don't have time to teach that one now. Just do a branch system. When you have loops, you assume those loops to be redundant. Maybe next week I'll discuss that. So that is that. So this is the end of the class today, and this is I will ask us to go and fill this table, please. We have designed for 13. We got here 0.58. We have designed for 7. We got 0. I can't remember what we got. Then the diameter is about something. This, the diameter. So once you do it to get this 2, you now go to your design, your AutoCAD drawing, and then impute it and draw it by the side of the pipe, indicating the slope, indicating the diameter, and of course, from the surveyor, you can see the nodes. So maybe tomorrow or next week, sorry, I will show us a typical design, how it looks like. So what all we need to do is for us to study, where is it again? The material we have downloaded. ABC design, I think I've shared with us. Wow, I shared the wrong thing, but I think it's still there with us, it's still there in that material. So the right thing is the ABC material, and not what I have here.
What we downloaded. That's what I downloaded.
ABC Estate. Thank you.
Yes.
ABC Estate, please open it. That's the right one. Thank you for that observation. ABC Estate. So use it to fill our table, and that is where we'll call it a day today. And
sorry, before you